Morning, everybody. This is Chapter 3, Freefall Motion, and you may be asking yourself, why am I watching this on video? Well, it's because Mr. Mounts picked a bad day to come back to school. I feel absolutely horrible, but I want you guys to get the same opportunities the other classes got, so I don't want anybody to be behind. So that's why we are watching a video lecture. So hopefully you can hear me okay. I'm probably a little bit stuffy, but well, I guess it's better than nothing. So let's check out Chapter 3, Freefall Motion. Well, you may have seen videos of astronauts on the moon dropping various objects to test how gravity works in a vacuum. And you may have seen where they take a feather and a hammer, or in this picture right here, you've got a feather and an apple. And in a vacuum, they actually drop at the same rate because there's no air resistance. On the moon, there's no air, so there's no air resistance. So a feather doesn't just waft down, but it falls down at exactly the same rate. So the underlying principle behind this is the fact that gravity pulls on everything equally, regardless of shape or mass. And that's what our principle is right here. No matter how big or small something is, gravity pulls on it at exactly the same rate. Whenever it is let go or thrown up or dropped down or whatever, we say that it's in free fall. That's what this means right here, that as soon as it is released, then gravity starts pulling on it, whether it's released upwards or downwards or not at all. So I'm kind of actually going up the scale right here. Now, in real-world situations, this doesn't necessarily apply, only because on the Earth we have air resistance. And if you were to drop a feather and an apple, the feather would float down to the floor, whereas the apple would drop relatively quickly. But we don't want to have to figure in air resistance. So in a perfect environment where you have a vacuum, two objects of different size will be falling at exactly the same rate. We call the acceleration of gravity g, or lowercase g. That's this right here. Now, you would think that gravity is the same all over the Earth, and for the most part it is, but look down here. We have a bunch of different places on the Earth where gravity varies somewhat. Why is that? Well, it's because the Earth isn't perfectly round. The Earth is actually somewhat oval-shaped, so that's an exaggeration of the Earth, and there's the North Pole right here and the South Pole. And so some places on Earth are closer to the center of gravity, that's our CG right there, are closer to the center of gravity than other places are. Basically what I'm saying here is that as you get away from the center of the Earth, gravity affects you less. So if you were to go on top of a mountain, per se, you would actually weigh slightly less because gravity pulls on you less. If you go into outer space, of course, we've seen that gravity becomes virtually nothing because you're getting further and further away from the center of gravity. So for the most part, look at our values right here. Gravity tends to fluctuate around 9.8. We're going to use 9.81 meters per second squared as our acceleration of gravity. Now, since gravity is usually oriented in the down direction for us, or at least towards the center of the Earth, we're going to put a negative in front of that. But it operates at 9.81 meters per second. That means if something starts at rest and drops because of gravity, or is pulled down because of gravity, it will be falling at 9.81 meters per second the first second, and 2 times that is, I need to do that in my head now, 19.6 meters per second the second, and 3 times that the third second, and so forth. So this is the value we're going to use for gravity, 9.81 meters per second. Again, all objects experience this. There is no object that is immune to gravity or is pulled by gravity less. All objects, regardless of size, shape, or mass, is going to be pulled at 9.81 meters per second. Again, the key phrase here is near the surface of the Earth. If you go up into the air, that is if you climb on top of a mountain, that's going to be less because gravity is tugging on you less because you're getting further and further from the center of gravity of the Earth. But we're assuming we're going to be at or near the surface of the Earth, and if we go back one slide, it'll be at an average location, since all these locations vary a little bit. Your average location is going to be 9.81 meters per second squared. That's going to be your acceleration of gravity. So let's take this and let's apply this to the kinematic equations that we know already, that we talked about last chapter. Here we have an equation for displacement right here. What we call displacement, delta x, or simply x. That could be in any direction. X typically is in the horizontal direction, but since we're going to be talking about free-falling objects, let's call our displacement y. Y, that's a bad pun, well, because y is vertical, and things tend to fall vertically. And so we'll think of our displacement now as in the vertical position. So that's up and down is going to be our y direction. So we'll call our displacement delta y. We still have an initial velocity, or we may not if it's 0. Time is still our time of falling. And now look here, our acceleration has been replaced with g right here. Remember we said before that g is going to represent the acceleration of gravity, g for gravity. But why is this negative? Over here it's positive, right? Well, because acceleration of gravity is going to be working in the downward direction. If we take down towards the Earth as negative, then that's how gravity accelerates things. It accelerates things downwards or in a negative direction. So if we think up towards the sky, here's your house right here in a tree. If that's positive, then that's going to be negative. Since gravity pulls things downwards, it's going to be negative 9.81 meters per second squared. That's going to be our gravity. Well, the same thing is true of our other equations, our other kinematic equations. We have a final velocity, an initial velocity, and acceleration and time. Well, they all stay the same, but acceleration gets changed to minus gt. Remember, acceleration is going to be negative 9.81 meters per second squared. If you take 9.81 as the magnitude, it's going to have a negative in front of it because it's negative 9.81 meters per second. And the same thing is true down here. Initial velocity and final velocity are going to be virtually the same, but we have a negative, and that's because our g, or our acceleration, is negative. And of course our displacement has been changed from change in x to change in y. They're virtually the same equations, but we have put some minuses in there because we're dealing with a negative acceleration. We call that g. So, we have similar equations that we talked about last chapter. And in fact, let me see, can I erase that? I can't. Well, I'm just going to go on. Remember that this displacement is equal to the change in the change of displacement. The final displacement minus the initial displacement is equal to the change. And so since we take this from the previous slide and we just break it apart into its two components and move the initial displacement over there, we're going to have a quadratic equation. If you look at it, you've got your a right here and your b, because remember it's a x squared plus bx plus c, and that's what this means down here. That our constants, the g, that is, sorry, the a value is going to be negative 1/2 g, because remember we have a 1/2 in front of our acceleration right here, and since the g is negative, it's negative 1/2 g. Here we have our initial velocity, if there is any. That would be your b value, and your initial displacement is going to be c right here. That may be 0 as well, but we at least are going to have an acceleration. We're always going to have an acceleration. So if we have a position versus time graph, so I'm going to call it y versus t, it should always be a downward opening parabola. Why? Because the acceleration is negative. And so whether it's something dropped from this location, it will curve down, or if it starts by being thrown upwards, it will always curve down, but it's going to be having a negative or downward opening parabola. That's our position versus time graph. Of course, velocity with respect to time is going to be linear. We have a linear relationship here. And so as time increases, your velocity is going to increase on a linear basis. So if we have, let's see, it's a very bad graph. That's time, that's velocity right there. Oh, and in fact, I should draw it like this. What's our acceleration? Well, it's negative g, right? So our acceleration, and I should draw this with another color. Let's make that blue right there. Or green, I guess. Not only am I sick, but I'm apparently colorblind too. That negative g is going to be, negative g is going to be our acceleration. So velocity versus time is going to be linear, but it's going to be linear on the order of whatever the acceleration of gravity is. In this case, it's negative 9.81. Whatever the initial velocity is or was is going to be our y-intercept. Now right here we're assuming initial velocity is 0. But you could have a starting positive or negative initial velocity, in which case that would be your y-intercept as well. And just like the last graph is always going to be a downward opening parabola, this graph will always be a downward sloping line. Why? Again, because the acceleration, or that is the relationship between velocity and time, is negative. And so we're going to have a negatively sloping line, downwardly sloping with a slope of negative 9.81. Let's change back to red here. Okay, so let's do a couple examples, and then that'll wrap it up for us. In fact, I'm going to have to save this till later because the bell just rang, and I run out of time right now. This is all the further we're going to go in our notes today. But we have example 1, 2, 3. Actually, we have 5 examples right here. What I want you to do is look at example 1 and 2 for tonight. That's going to be your homework for tonight. Now, again, I may or may not check it tomorrow, but I assume that I will. And what I'm going to do my best to do this afternoon, if I do wind up going home from school, because I do feel horrible, is I'm going to record more videos of this when I get home. So you can try it on your own time, and then if you get stuck, or if you want to check the right answer, check it against what I have and see if you got what I got. So look at examples 1 and 2. You're welcome to work in class with somebody else or on your own, and check them against what I have. Again, I will, like I said, I'll do my best to put this on the site, but I'd like you to at least have looked at them, at least. So that's it. Thank you for listening. I'm sorry for not being here in class, but hopefully this will do in the meantime, and I'll see you when I get back. Bye, everybody.